There's a moment right before a strike where the whole world feels like it's holding its breath. The wind shifts. The streetlights buzz a little louder. You smell rain, metallic, sharp, like the air itself has teeth. And then the question hits harder than the thunder. If we can forecast hurricanes and land probes on Mars, why can't we point to the exact place the next lightning bolt will land? We're outside right now. Not in a studio, not in a diagram, out here where the storm is arriving like a living thing. The sky has that layered, bruised look, blue-black in one direction and sickly gray in another. You can feel the humidity on your skin, and the hairs on your arm don't quite know what to do with themselves. A low growl rolls across the clouds, and you reflexively count. 1, 2, 3, 4, then the crack. That distance calculation, sound lagging light, is something a child can do. So why does the most important calculation stay out of reach? Not, how far away? Not, is this storm dangerous? But, which exact spot becomes the chosen one? Because lightning isn't just spectacle. It's fatalities. It's wildfires. It's hospital wards filling with burns and cardiac arrests. It's airport shutdowns, ruined transformers, shattered trees, and entire neighborhoods going dark in a single instant. It's also, in a strange way, a decision, a physical decision made by air and ice in charge. And it feels deeply unfair that a storm can be so consistent in its patterns and yet so unpredictable in its final, lethal gesture. So this is the audit. We're going to follow the charge. We'll trace it from the first collision between tiny pieces of ice to the first invisible step of a lightning leader. And we're going to be honest about where certainty breaks, not as a failure of science, but as a clue about what reality is like when it's dense, fast, hidden, and right on the edge of change. Come closer. Imagine we could peel back the cloud like a curtain without disturbing it. The first shock is that a storm isn't a vague, misty blob. It's a machine. A heat engine built from sunlight and water, running on the simple fact that warm, moist air wants to rise. Down here near the ground, air is heavy with water vapor. The storm's updraft grabs it, sometimes at tens of meters per second, and drags it upward like an elevator that doesn't stop at any floor. As the air rises, pressure drops, it expands, and it cools. Water vapor condenses into droplets. And as that air keeps climbing, the world inside the cloud stops being just liquid. It becomes a vertical city of phases. At one altitude you have liquid droplets, soft, round, obedient to airflow. Higher up you have ice crystals, delicate, angular, glittering in theory, though you'll never see them individually because the cloud is opaque. Somewhere in between, you have slush-like particles, half-frozen, irregular. And then there's graupel, think of it as snow pellets with an attitude. Little ice balls formed when supercooled water droplets slam into a snowflake and freeze instantly, building a lumpy coat. Graupel is heavier than delicate crystals. It falls more readily, but updrafts can still toss it around like a pinball. If you've ever watched a lava lamp, you've seen something like this. Blobs rising and falling, mixing, exchanging. But in a thunderstorm, the blobs are billions of particles, and the mixing is violent. Everything collides with everything. And here's where the storm begins to charge itself. We need a metaphor, but we also need precision. Most people learn static electricity by rubbing a balloon on hair. Charge is separate. One thing steals electrons, the other loses them. The storm does something similar, but instead of a balloon in your scalp, it has graupel and ice crystals colliding inside turbulent airflow, over and over, across cubic kilometers. In these collisions, charge gets exchanged. The exact microphysics can be subtle. Temperature matters, liquid water content matters, how fast they collide matters, but the big picture is brutally simple. The storm sorts electric charge the way a river sorts sediments. Lighter ice crystals tend to get carried upward by the strongest updrafts. Heavier graupel tends to fall or hover lower. And through countless collisions, the cloud builds regions where one sign of charge dominates. Often, though not always, the mid to lower part of the cloud becomes strongly negative. Above it, the upper cloud becomes positive. Sometimes there's an additional positive region near the bottom. Sometimes the structure is layered like a complicated cake, plus, minus, depending on storm type and dynamics. It's not a neat battery. It's a living, shifting architecture. Now pause and let the numbers land. When we say charged cloud, we're not talking about a mild static cling. We're talking about electric potentials that can climb into the hundreds of megavolts. In some scenarios, approaching gigavolt scales across distances of a few kilometers. A gigavolt is a billion volts. That's the kind of number you associate with particle accelerators and laboratory nightmares. And the storm is assembling it out of air and water. So why doesn't it just discharge continuously the moment it gets a little too charged? Why does it wait, and then suddenly tear the sky open? Part of the answer is that the sky is full of lightning you never see. Before a cloud-to-ground strike ever happens, storms crackle internally. There are intra-cloud discharges, lightning that stays inside the cloud. There are cloud-to-cloud discharges that jump between charged regions. There are brief luminous events so fast or so hidden that your eyes miss them, but instruments don't. Bursts of radio emission, faint optical flashes, tiny discharges that die before they become dramatic. A thunderstorm is not quiet. It's a constant negotiation of charge. But the kind of strike we fear, the one that reaches the ground, requires something special. It requires the air to fail like a dam breaking. And now we arrive at the edge of what we know, and the edge of what the storm is doing. Because air, under normal conditions, is an insulator. It's the reason you can stand under power lines without immediately becoming part of the circuit. To make air conduct, you have to rip electrons off molecules and create a path of ions and free electrons, a plasma channel. In a textbook, there's a number for breakdown field, the electric field strength needed to make uniform air suddenly conduct. It's large, on the order of millions of volts per meter. In a simple, uniform gap between electrodes, you can measure it. But in real thunderstorms, when researchers estimate the average electric fields across large volumes, they often get values that look too low. Too low to break down air in the clean, uniform, textbook way. And yet lightning happens anyway. That mismatch is a doorway into the true complexity. Because lightning is not one continuous spear of electricity that forms all at once. It is built. It is assembled step by step, like a nervous system growing its own path through darkness. If we could freeze time and watch the first moments of a cloud-to-ground strike, we wouldn't see a single bolt. We'd see a faint, branching, invisible exploration descending from the cloud. This is the leader, a precursor channel of partially ionized air. And here's the part that feels almost uncanny. The leader doesn't move smoothly. It steps. It advances and jumps, tens of meters at a time, then pauses, then jumps again. Each step is like the storm reaching forward with a probing finger, feeling for a route that will work. It branches, too, splitting into multiple tendrils. Most of those branches will die. One will win. So lightning isn't aimed at a target in the way a thrown spear is aimed. It's more like a root system searching for water in dry soil. Or like a crack spreading through stressed glass. It follows laws, but it also follows opportunity, tiny imperfections, tiny fluctuations, tiny advantages that explode into destiny. And here's where the prediction dream starts to slip. Because the decisive factors aren't just the large-scale ingredients, warm moist air, a strong updraft, plenty of ice. The decisive factors are microscopic and fast and hidden. They live in the storm's smallest volumes, in the exact arrangement of particles and fields that we cannot directly observe in real time. Let's make that concrete. Inside the cloud, the electric field isn't smooth. It's jagged. It spikes near objects. A sharp point concentrates electric field. This is why lightning rods work, and why your hair stands up near high voltage. Inside a thundercloud, you have countless points, edges of ice crystals, irregular graupel surfaces, tiny water droplets, and even turbulent pockets where charge density becomes locally extreme. Each of these can enhance the local electric field far above the average. So even if the storm's average field looks too weak for breakdown, there may be tiny neighborhoods where it's intense enough to start something. But start what, exactly? How do you go from a region where electrons are slightly encouraged to move to a self-sustaining leader channel that can cross kilometers? One candidate is what researchers call runaway breakdown. Let's translate that without losing its bite. Normally, if you push an electron through air with an electric field, it collides with molecules and loses energy. It's like trying to sprint through a crowded room. You keep bumping into people. You don't accelerate much. But in strong enough fields, a fraction of electrons can run away. They gain more energy between collisions than they lose. They become fast, so fast that relativistic effects can matter. And as they plow through air, they knock loose more electrons, creating an avalanche. A relativistic runaway electron avalanche. The name is a mouthful, but the picture is simple. One electron becomes many, and the many become a conductive seed. Where do the first fast electrons come from? Sometimes, from cosmic rays. Yes, particles from space, born in violent astrophysical events, raining down through the atmosphere. Most pass through you unnoticed. But occasionally, they can ionize air in a way that provides the initial spark, the seed for an avalanche under the right electric conditions. And now you feel the unease of it. A storm is building a colossal voltage like a charged heart. Its internal structure is turbulent, layered, constantly rearranging. And the final trigger might depend on a microscopic field enhancement near a single grapple pellet, plus the random timing of a cosmic particle from deep space, plus the exact humidity and temperature at one altitude, plus the branching history of a leader that hasn't even formed yet. So when someone asks, "Why can't we predict exactly where lightning will strike?" they're asking for a level of knowledge that would require seeing the storm's hidden microstate, the exact configuration of charges and particles in 3 dimensions, at millisecond timescales. It's like trying to predict the exact location of the next crack in a piece of glass while the glass is still being made, while it's vibrating, while it's being heated and cooled unevenly, while you're only allowed to watch its shadow on a wall. And yet we haven't stopped trying. Because humans don't accept unpredictable easily, not when the stakes are life and infrastructure. So we've built eyes and ears for storms. We've built arrays that listen to lightning and radio frequencies, because leaders and discharges emit bursts of electromagnetic energy. We've built lightning mapping arrays that triangulate VHF emissions and reconstruct the 3-dimensional geometry of lightning inside clouds like a kind of CT scan made of radio waves. We use VHF interferometry to get fine-scale timing and direction, watching the leader's growth with astonishing precision. We put optical sensors on satellites, like the geostationary lightning mapper, that can see lightning flashes from orbit, mapping their frequency over entire continents. We deploy fast electric field sensors, field mills and antennas, that measure rapid changes in the local electric environment. And yes, we apply machine learning, training algorithms on vast datasets, radar signatures, atmospheric profiles, lightning history, storm morphology. We ask the models to tell us which storms are likely to produce lightning, when the risk is rising, where the probability is highest. These tools work, up to a point. We're getting better at predicting lightning likelihood in a region, better at identifying dangerous storms, better at issuing warnings that save lives. But exact strike point, seconds ahead, is a different beast. Because by the time a leader is stepping downward, the decisive geometry is forming in real time, inside a cloud that is optically opaque and electrically complex. And then comes the moment that flips your intuition completely. Because even if you imagine the leader descending like a vine from the cloud, choosing its target, that's not the full story. The ground is not passive. As the descending leader approaches, the electric field at the surface intensifies. Tall objects, trees, buildings, antennas, ridgelines, begin to launch upward streamers, faint, rising tendrils of ionized air reaching up to meet the leader. So the final strike point is often chosen late, in the last tens of meters, through a kind of rapid negotiation between sky and ground. The leader is searching downward. Multiple points on the ground are reaching upward. And the one that connects first becomes the path for the massive return stroke, the blinding flash we call the lightning bolt. That changes the whole emotional texture of the question. Because the bolt you see is not the beginning. It's the victory lap. It's the moment the circuit closes and an enormous current surges upward through the established channel, heating the air to temperatures hotter than the surface of the sun, expanding it explosively into the shockwave we hear as thunder. But the decision happened in the invisible prelude, in the stepping leader, in the branching failures, in the upward streamers rising from the ground like desperate hands. So when you ask for the exact strike point, you're asking to predict the outcome of a high-speed, high-dimensional negotiation between a chaotic cloud and a complex landscape, mediated by physics that sometimes depends on microscopic randomness. Now let's stress test our reality model. We love the idea that the universe is deterministic, that if you know the laws and the starting conditions, the future is fixed. In many settings, that works beautifully. We predict eclipses centuries ahead. We calculate spacecraft trajectories. We model weather patterns days out with increasing skill. But lightning lives at a boundary where deterministic laws can produce outcomes that feel probabilistic, because tiny differences amplify fast, and because we can't observe the necessary detail in time to compute the result. This is not a retreat into mysticism. It's a deeper honesty about prediction. Prediction isn't just about having the right equations. It's about having the right information and being able to access it before the event happens. A thunderstorm is a computational system, in a sense. Not a computer made of silicon, but a computer made of fluid dynamics, phase transitions, and electromagnetic forces. It processes energy and charge. It evolves. It computes its next state. But it computes privately. Its most important variables are inside an opaque volume of cloud, changing faster than our sensors can map with full resolution. So the limitation isn't only, our models aren't good enough. The limitation is also, the system doesn't reveal enough of itself quickly enough for any external observer to predict the precise outcome. And that's a strange kind of comfort if you let it be. It means the storm isn't capricious. It's lawful. But it's lawful in a way that still leaves room for surprise at the local scale. Like a melody played perfectly from the same sheet music, but with improvisation in the micro-timing, enough to change which note lands exactly on the beat. So what can we predict reliably? We can predict environments conducive to thunderstorms. We can identify storms with strong updrafts and mixed phase regions, ingredients that favor charge separation. We can map where lightning activity is increasing. We can give probabilistic forecasts. This county has a high chance of cloud-to-ground strikes in the next hour. This ridge line is a high-risk zone. This sporting event should be delayed. We can design protection, lightning rods, grounded systems, surge protectors, safe building codes. And we can teach behavior. If you hear thunder, you're within striking distance, because lightning can strike far from the rain core. But the exact strike point, the exact tree, the exact fence post, seconds before it happens, often remains intrinsically hard. Not because physics is broken, but because the final choice is made late, inside the leader-streamer dance, shaped by microstructure and chance. Which brings us back to where we began. We're still outside as the storm advances. The first drops hit the pavement, and darken it in coins of wetness. The wind pushes the trees into a synchronized shiver. Somewhere beyond the clouds, charged layers are stacked like invisible tectonic plates, negative below, positive above, maybe more layers hiding. Leaders are preparing, stepping in darkness. And the ground, quietly, is ready to reach up. If you stand here thinking lightning is just a bolt from the sky, you feel small in the wrong way, like you're powerless because the universe is arbitrary. But if you stand here knowing what's really happening, you feel small in the right way. You're watching an immense natural machine balancing on the edge of insulation and plasma. You're watching order and turbulence collaborate. You're watching a lawful universe produce outcomes that no single observer can fully foresee. So here's the synthesis, what we've earned on this walk into the storm. Thunderstorms build vast voltages through collisions of ice and graupel, sorting charge into layered regions across kilometers. Lightning doesn't require the entire cloud to exceed textbook breakdown fields because local enhancements, turbulent charge pockets, and runaway electron avalanches can create conductive seeds. A strike is not a single, smooth event, it is constructed by stepping, branching leaders. And the final attachment to ground is often decided late, when upward streamers rise to meet the descending leader. That target is a negotiation, not an aim. Now take this with you as a thought experiment. Imagine you had perfect knowledge of the storm at large scale, radar, satellite, electric field sensors, everything. But you're missing only one thing: the exact location of a single tiny pocket where the electric field spikes around an ice particle at just the right millisecond. In one timeline, that pocket seeds a leader branch that survives. In another timeline, it doesn't. And the bolt lands 50 meters away, enough to kill someone standing under the wrong tree, or spare them entirely. How much of your life, outside storms, is shaped the same way, by systems that are lawful but locally unknowable until the last second? And that opens the next great question. If nature can be perfectly physical and still surprise us, if prediction is limited not just by intelligence but by access to information, what does that say about the way we think about control in our own lives? If you want to keep going, I'm putting another investigation on your end screen. Watch that next, because it pushes this same boundary between what we can calculate and what we can only live through. And I want to hear one simple answer from you in the comments. Have you ever been close to a lightning strike? Close enough to feel it in your body? And what did it change about the way you see storms? If you're here for science that doesn't just explain, but audits reality with you, subscribe. Not for notifications, but so we can build a library of questions that make the world feel bigger, clearer, and more honest every time you step outside under a charged sky.